Hi everyone, in this video we're looking at another example involving exponential growth. So here we're told a biologist makes a sample count of bacteria in a culture and finds that it doubles every 3 hours. The estimate count after 6 hours was 10,000. So here it says what was the initial size of the culture. Now, since let's introduce some variables. Let's let n of t represent the number of bacteria as a function of time. As a function of time t in hours. So n of t is the number of bacteria as a function of time in hours. Let's also think about how we could get the initial size of the culture. So here it says that the bacteria double in size every 3 hours, or the number of bacteria double every 3 hours, and the estimate for the count after 6 hours was 10,000. So how many times did after 6 hours, how many times did the bacteria double? And the answer to that is we could just divide 6 by the doubling period, which is just equal to 2. So the population of the bacteria had doubled twice. So that means that we can just take 10,000 and divide it by 2 twice. So we're dividing 10,000 by 2 squared. 10,000 divided by 2 squared is just 10,000 divided by 4, which is just 2,500. So therefore, there were 2,500 bacteria initially. Therefore, there were 2,500 bacteria initially. Next, it says what was the estimated count after 1 day. So here we could figure out how many times the bacteria doubled, and then just multiply the initial quantity by the number of times that it doubled. But it's probably just easier to come up with a function for to represent and model this growth. So here n of t represents the number of bacteria as a function of time in t hours. So I know that I'm going to multiply the initial amount, which was 2,500, by 2 every time the bacteria doubles. So we have to figure out how many times, how we can represent this equation in terms of t. And if I think about this, if I just plug in t here, right now, after 1 hour, I would double the population. So I have to make sure that this just doubles every 3 hours. So when t gets to 3, I'm only going to multiply 2,500 by 2 once. So I have to divide t by the doubling period, which is 3. So I'm going to have 2,500 times 2 to the power of t divided by 3. Let me write that out a little bit bigger so you can see it. So this was n of t is equal to 2,500 times 2 to the power of t divided by 3. And the reason being is that because the population of the bacteria is just going to double every 3 hours. So when t gets to 3, we should have 2 to the power of 1. When t gets to 6, we should have 2 to the power of 2. When t gets to 9, we should have 2 to the power of 9. And if you want to make a table of values for this, you can see that that's exactly what this equation gives us. So now we can use this equation to calculate what the estimated count was after 1 day. And just as a quick refresher, in one day there are 24 hours. So our equation is in hours, so I can't just plug in 1 for t, because that would be in days, whereas I need this to be in hours. So I'm going to evaluate n of 24, which is equal to 2,500 times 2 to the power of 24 over 3 24 divided by 3 is just 8, so I'm going to do 2,500 times 2 to the power of 8. And if you calculate this, you get that this is equal to 640,000. So therefore, after 1 day, there are 640,000 bacteria. Now, one thing to note here is that when you're dealing with exponential when you're modeling naturally occurring phenomenon with exponential functions, one thing to note is that the functions often have a limited domain. So obviously, if the bacteria kept doubling, every 3 hours for for a year, the culture would probably be larger than the mass of the Earth. So, and for other reasons, the bacteria would die before that. Like they would run out of food and resources. That life would be unsustainable for the bacteria. So this function, it only models the growth of the bacteria for a limited period of time. The bacteria can't continue to just double every 3 hours like this indefinitely. It's just not physically possible. So here it says what was the count after 1.5 hours. So here we're going to evaluate n of 1.5. And this is equal to 2,500 times 2 to the power of 1.5 over 3. This is equal to 2,500 times 2 to the power of 1/2. But 2 to the power of a half is just root 2. So I would have 2,500 times root 2 bacteria. And here, this is actually an irrational number. So I can go ahead and I can convert it to decimal, because obviously I won't have an irrational number of bacteria. You get that this is equal to 3,536 approximately. So this rounds to 3,536. So therefore, after 1.5 hours, there were 3,536 bacteria. Another thing to note is that we've kind of set these equations up, and we've done this just by using logic. But in general, if a function is modeled by exponential growth, and we know its doubling period, and we know its initial amount, then the number or the quantity as a function of time is equal to n sub 0, or n subscript 0, times 2 to the power of t over, let's just call this td. Okay, so this, let me write this out so it's a little bit larger. So we have n subscript 0, which is the initial amount. So let me write that out. Initial quantity times 2 to the power of t over t subscript d, where d is the doubling period. And in the example above, it's better to kind of understand this equation than it is to just memorize it, because if you memorize it, chances are you'll forget what it is, or you won't understand it, and you won't know how to apply the actual formula. So it's better in math to be able to sort of piece together an equation by using logic, and sort of figuring out what you know and how the information that you're given pieces together. In the next video, we'll start exponential decay.